Hi everyone, and again welcome to the School on Spectral Methods for Complex Systems. Today I'm going to present the second part dedicated to iterative linear solvers. In particular, if you don't remember, the topic of my set of lectures is about the study and the development of deterministic and stochastic acceleration techniques for Richardson type iterations. As I already mentioned in the previous lecture, the goal is to develop efficient and reliable algorithms to solve highly dimensional linear systems that are progressively towards exascale, moving towards exascale. And the goal is to efficiently and reliably solve these sparse linear systems in parallel. Efficiency requires communication reduction, and usually this comes along with scalability. That is the ability of an algorithm to handle a growing amount of work. When communication reduction and scalabilities are obtained, then the algorithm is claimed to perform efficiently in a parallel computing framework. And we already focused on deterministic accelerations for Richardson type iterations that aim to attain efficiency. In this second part, instead, we're going to focus on stochastic accelerations for Richardson type iterations in order to obtain reliability, robustness against the occurrence of faulty phenomena. In other words, what is also named resilience. And so for this, I'm moving directly to slide number 47, which is where indeed the study of resilience is going to be kicked off in this lecture. Resilience, as already said, is the ability to compute a correct output even in presence of faults, of faulty phenomena. I already mentioned the fact that faults can be hard or soft. Usually, a hard fault occurs when there's a power loss or the crash of a computing node. Whereas a soft fault is more difficult to detect, and it's usually related to phenomena like bit flips, or usually caused by cosmic radiations that interact with the chips. And these soft faulty phenomena um, cause the computer to provide a wrong answer without actually declaring that something went wrong. And so soft faults are trickier because they are more difficult to detect. Um, an algorithm that can address and be robust against hard and soft faults is called resilient. Different approaches have been tried in literature to come up with resilient algorithms. Mainly, the idea again was to start with Krylov subspace methods like conjugate gradient, GMRES, or BCG step, and readapt these algorithms to improve their robustness against faults by recover restart strategies such as checkpoint strategies. However, results in these path have been somewhat limited. Therefore, um, scientists proposed also the opportunity to investigate and explore alternative paths like the abandonment of deterministic paradigms in favor of stochastic approaches. And indeed, this is the main scope of this current lecture. Again, we are going to consider a sparse non-singular linear system, Ax equal to b, and differently from the lecture number 1, in this case, we want to highlight the possibility of a left preconditioner. In this, if a left preconditioning is applied, then the linear system in equation number 14 becomes a preconditioned linear system as shown in the equation number 15. P inverse Ax equal to P inverse B, where P inverse indeed is the preconditioner applied to the linear system of interest. Again, equation number 15 can be recast as a fixed point scheme in equation number 16, where we have x equal to h times x plus f. H is the iteration matrix associated with the fixed point iteration. In this case, since we explicitly present the preconditioner, H is the identity minus P inverse A, and F is the preconditioned right-hand side, P inverse times B. Again, we remind you that a fixed point iteration converges to the exact solution in exact arithmetic if and only if the spectral radius of the iteration matrix is less than 1. And the solution to the linear system of interest, the vector x, can also be written in terms of a power series in H, the so-called Neumann series, where essentially the solution vector x can be written as the sum of h for L that goes to 0 to infinity of h to the power of L times f, the preconditioned right-hand side. If we look at the Neumann series entry-wise, that is, if we rewrite the Neumann series for the ith entry of the solution vector x, then the Neumann series becomes the equation in formula number 17. The idea of stochastic approaches to accelerate fixed point iterations is to reinterpret formula number 17 as the expected value of an estimator defined in terms of random walks. Since the goal is to define an estimator that is based on random walks, first of all, we must introduce what a random walk represents for us. As any other statistical quantity, a random walk needs to be defined on a state space. And in this case, the state space capital S is the set of indices of the forcing term f. Therefore, S is the set of integer numbers that go from 1 to n, where n is the dimensionality of the linear system that we want to solve. Then we must also, in order to define properly the random walks, we need also to introduce the initial probability. And in this case, at first we focus on picking the ith state as the initial state of the random walk. So in this case, we can say that the initial probability is a Kronecker delta that is that gives probability equal to 0 to all the entries except for the ith entry where the probability is equal to 1. Moreover, we must also introduce the transition probability that allows us to establish the policy to explain the way a random walk transitions from a state to the successive one. And in this, at first we consider as transition probability or transition matrix the L1 normalization of the iteration matrix. Sorry, the L infinity normalization, the row-wise normalization of the iteration matrix, as it is shown at the very last formula in slide number 50. Once we have defined the state space, the initial probability, and the transition matrix, we need also to introduce two sequences of weights in order to build the estimator. The first sequence of weights is defined by lowercase wij equal to the entry-wise ratio between the ijth entry of the iteration matrix and the ijth entry of the transition matrix. And once we have defined this initial sequence of weights, we use this sequence to build a secondary auxiliary sequence of weights whose recursive definition is shown at the center of slide number 51, where capital W0 is essentially the ratio between the vector h k0 over p tilde k0. And here we remind you that the vector h and the vector p tilde right now are supposed to be arbitrary vectors. I will explain to you later what these vectors represent. Then the capital Wi weight is defined recursively depending on the I-1. This new sequence of weights allows us to introduce a statistical estimator defined on these random walks, and it can be proved that the expected value of the statistical estimator of interest is equal to the summation represented in formula number 18. You can notice that the right-hand side of equation number 18 is a statistical representation of formula number 17. Indeed, you can identify lots of similarities between formula number 17 and formula number 18. In particular, in formula number 18, you have extra terms related to the probability, because in this case, of course, the goal is to compute the statistical estimator, the expected value of the statistical estimator, and so the probability plays a role. But essentially, you can reinterpret the formula number 18 as a statistical reformulation of the deterministic formula shown in equation number 17. This generates a statistical estimator associated with a method called forward or direct Monte Carlo method to statistically model the Neumann series. The drawback of this method is that the estimator in formula number 18 is defined entry-wise. What this means is that a single set of random walks is employed only to reconstruct a statistical estimation of a single entry of the solution vector. If one person wants to use the forward direct method presented here to reconstruct the entire solution vector, then the user must employ n sets of random walks. Using n sets of random walks is extremely expensive, and for linear systems of interest nowadays that are moving towards exascales, this computational cost is unaffordable. This is the reason why in literature people came up with an alternative Monte Carlo technique called adjoint method. This method is called adjoint because its derivation is obtained considering the adjoint linear system to the one of interest. The adjoint linear system is shown at the top formula in slide number 52. And again, in order to derive this new adjoint Monte Carlo method, we reinterpret the adjoint linear system as a fixed point iteration, as shown at the formula as shown in the formula at the center of the slide number 52. In this case, we pick the vector d as a vector of the canonical base, and through some algebraic relationships between quantities associated with the primal linear system and quantities associated with the dual linear system, we can prove that the functional J star defined on the solution to the adjoint system equal to the inner product between y and f can be rewritten as the inner product between the solution to the primal linear system and the jth vector of the canonical basis. And this is equal to the jth entry of the solution vector x. In this case as well, we introduce the initial probability and the transition matrix as we did for the forward problem. If you remember, I put you on hold earlier when I mentioned the presence of the vector p and the vector h. For the forward method, the vector p tilde was a Kronecker delta. In this case, the vector p tilde is not a Kronecker delta anymore. It's actually the L1 normalization of the preconditioned right-hand side, as shown at the left top, as shown at the top left of slide number 53. Whereas at the top right, we have the definition of the transition matrix that resembles the definition of the transition matrix for the forward method. However, in this case, we replace H with H transpose because of the adjoint nature of the linear system from which the adjoint method is derived. Again, we introduce the two sequences of weights, lowercase w and uppercase w, and these two sequences of weights allows us again to introduce an estimator associated with defined in terms of random walks. However, differently from formula number 18, the statistical estimator in formula number 19 is a statistical estimator that allows us to reconstruct the entire solution vector. Therefore, the statistical estimator associated with the adjoint method gives us the advantage of employing a single set of random walks to define the entire solution vector, instead of using n sets of random walks as the forward method required. This will represent a significant reduction in the computational in the computation required in order to reconstruct the solution vector of interest. However, all the techniques that we have proposed so far, both the forward and the adjoint method, rely on statistical quantities, statistical variables, to reproduce and reconstruct the solution to a linear system. Every time statistical quantities are employed, it's very important to guarantee that the statistical quantities are well defined. In this case, the statistical estimator, that is a random variable, is well defined if and only if both the expected value and the variance are finite. And this is important in order to apply the central limit theorem. The central limit theorem guarantees us that increasing the number of samplings, we asymptotically improve the accuracy associated with the statistical estimation. But in order to have this guarantee, expected value and variance must both be finite. The finiteness of the expected value and of the variance, both for the forward method and for the adjoint method, have an algebraic reinterpretation. In particular, as shown in the formulas at the center of slide number 54, the finiteness of the expected value is equivalent to having the spectral radius of the iteration matrix less than 1. However, we know that this is not enough. We must require also the finiteness of the variance. And here it is shown that the finiteness of the variance is equivalent to requiring the spectral radius of h hat be less than 1, where h hat is a new matrix introduced at the top of slide number 54. And again, the entry-wise definition of h hat varies according to either the forward method or the adjoint method. In general, we know that the finiteness of the variance always implies the finiteness of the expected value, because the finiteness of the variance coincides with the finiteness of the second moment of a statistical estimator. And if the second moment of a statistical estimator is finite, then also the first moment of the statistical estimator is finite as well. This can be recast algebraically, saying that if the spectral radius of h hat is less than 1, then this automatically implies also that the spectral radius of h is less than 1. At the beginning, I told you that the deterministic fixed point iteration was guaranteed to converge to the exact solution of the linear system of interest if and only if the expected radius of h is less than 1. Here I'm saying that the statistical version of the fixed point iteration converges to the solution of interest if and only if the spectral radius of h hat is less than 1. Essentially, what I'm telling you is that the set of cases, the class of problems for which the stochastic fixed point iteration converges, is restricted with respect to the class of problems for which the deterministic stochastic is restricted with respect to the class of problems where the deterministic fixed point iteration is guaranteed to converge. Therefore, going from the deterministic to the stochastic version of the fixed point iteration, we are losing generality, because we are restricting the case on which the scheme is guaranteed to converge. The first attempts to apply Monte Carlo techniques to solve sparse linear systems go back to the 1960s, and the advantage of these techniques are represented by the fact that Monte Carlo approaches are embarrassingly parallelizable, because all the statistical samplings are independent from each other, and therefore they can be easily parallelized and split on different processes. However, because of the central limit theorem, the amount of work required to attain a prescribed accuracy is generally unaffordable, because essentially the error associated with the estimation scales as 1 over square root of n, where n is the number of statistical sampling employed. Therefore, in order to employ statistical fixed point iterations on state-of-the-art problems, it is important to accelerate these stochastic techniques through some expedients. Thomas Evans and his collaborators proposed an acceleration for the stochastic fixed point iterations described as Monte Carlo synthetic acceleration. The pseudocode of the MCSA is shown in slide number 56. The idea here is to alternate a deterministic fixed point iteration with a stochastic fixed point iteration. The deterministic fixed point iteration is the step represented in red, whereas the stochastic fixed point iteration is enclosed in the green box. I wanted to remind you that here the goal is to employ statistic techniques to obtain resilience, or to increase robustness against faulty phenomena. Because of this, the ideal will be to spend as much time as possible inside of the green box, which means spending as much time as possible computing the stochastic acceleration, and spending as little time as possible outside of the green box. The reason why this is important is because, as we already said, Monte Carlo approaches are embarrassingly parallelizable, and if a few processes compute some statistical samplings incorrectly, either these statistical samplings computed incorrectly can be discarded, or their impact may be damped by the averaging over all the statistical samplings performed. And therefore, the Monte Carlo approach is very appealing to address both hard faults and soft faults. Addressing the hard faults is easy because essentially the statistical samplings that are lost are simply neglected, and the statistical samplings associated with soft faults can be sort of hidden or damped in their impact by the computation of the average that is required to compute the expected value. In a natural question that my advisor and my collaborators and I asked ourselves was the following. Okay, we have these statistical techniques. We know that in order to provide an estimation of the solution vector, these techniques require performing some random walks, but the question that comes natural is how many random walks do we need to run to attain a prescribed accuracy? In order to answer this question, I introduced some statistical adaptive approaches that essentially progressively increase the number of statistical samplings employed until the apparent relative standard deviation drops below a prescribed accuracy, a prescribed threshold imposed by the user. Here in slide number 57, I present the definition of my adaptive criterion, both for the forward method and for the adjoint method. The idea is to find the number n tilde that guarantees the apparent relative standard deviation shown as sigma over absolute value of x, and the idea is to increase the number of random walks or number of statistical samplings until this apparent relative standard deviation goes below a threshold epsilon defined by the user. An important drawback that one person needs to keep in mind about the stochastic fixed point iterations is the fact that the iteration matrix H must be built explicitly. This is not necessary for deterministic fixed point iterations because if one person uses the corrective form of the fixed point iteration, then xk plus 1 is equal to xk plus rk, where rk is the residual. However, in order to define the random walks, the construction of the iteration matrix H is needed because the iteration matrix is used to define the transition matrix, and the transition matrix is defined entry-wise in terms of H. Therefore, H must be known entry-wise, which means that H must be explicitly built. And this represents an inconvenience because, of course, explicitly building H requires compromising the sparsity pattern of the original linear system of interest, because computing H means applying matrix products, and usually the matrix products disrupts the sparsity, compromises the sparsity. In order to have the matrix H sparse, we had to restrict the list of preconditioners that we could be focused on, because the only preconditioners that we can employ are those preconditioners that guarantee H to be sparse. And these the list of preconditioners that we limited to are diagonal preconditioners, block diagonal preconditioners, and sparse approximate inverse preconditioners. In particular, the sparse approximate inverse preconditioners that we focused on are the one is the INV sparse inverse that is described in some papers published by Michele Benzi, my advisor, Karl Mayer, and Miroslav Tuma in CISC in 1996. The sparse approximate inverse is a factorized preconditioner that essentially is represented by the application of three different factors, Z, D, and W, as shown at the very top of slide number 59. An important fact to notice is that the order in which these three factors are applied, which means applying these three factors to the left of A, or applying these three factors to the right of A, or splitting the factors so that D and W are applied to the left and Z is applied to the right, should not change the behavior for deterministic fixed point iterations, because all the three situations presented at the top of slide number 59 generate iteration matrices H with the same spectral radius. However, we know that the convergence of stochastic fixed point iterations is not dominated by H. It's dominated by H hat, and H hat changes entry-wise according to where the preconditioner is applied. Therefore, even if applying the preconditioners to the left or to the right doesn't change for deterministic iterations, it does impact the stochastic acceleration. In particular, there can be situations where applying the preconditioner on one side guarantees convergence, whereas applying the preconditioner to the other side does not guarantee convergence. And actually, there may be some situations where the scheme diverges. For the theoretical analysis of these techniques, our goal was to identify classes of problems for which stochastic fixed point iterations could be guaranteed to converge a priori. And this is possible on strictly diagonally dominant matrices, as shown by Srinivasan in a paper that he published in 2010, because if a matrix is strictly diagonally dominant, then the application of a diagonal preconditioner to the coefficient matrix allows us to build an iteration matrix H with infinity norm or one norm less than 1. And since H hat is defined entry-wise based on the iteration matrix and the transition probability, if you go back and look at how the transition probability was defined, you can see that it's easy to prove that the infinity norm of H less than 1 automatically implies the infinity norm of H hat less than 1. But if the infinity norm of H hat is less than 1, then also the spectral radius of H hat is less than 1. Likewise for the one norm. It's important to notice that the strictly diagonally dominance by rows guarantees convergence for the forward method, but it does not guarantee convergence for the adjoint method. Vice versa, strictly diagonally dominance by columns guarantees convergence for the adjoint method, but it does not guarantee convergence for the forward method. Of course, if a matrix is strictly diagonally dominant both by rows and columns, then both the forward and the adjoint methods are guaranteed to converge a priori. Another set of matrices on which the Monte Carlo linear solvers are guaranteed to converge a priori is the set of generalized diagonally dominant matrices. In particular, a very known subspace of generalized diagonally dominant matrices is represented by M matrices. Indeed, if a matrix is generalized diagonally dominant, then it exists a diagonal matrix D such that A times D is strictly diagonally dominant. And once the strict diagonally dominance is obtained via the matrix multiply A times D, we go back to the strictly diagonally dominant case that we already saw in slide number 60. Moreover, my advisor and I introduced a new concept. We tried to identify also other classes of problems on which the convergence could be guaranteed by applying a block diagonal preconditioner. In particular, we came up with these two conditions presented in formula in slide number 61, where essentially we proved that if a block diagonal preconditioner guarantees these two conditions to be satisfied, then either the forward or the adjoint method is guaranteed to converge combined with a block Jacobi preconditioner. These two formulas here have been described in the paper that we published on this topic, and it essentially generalizes a definition of block diagonally dominance for a matrix that was originally introduced by Feingold and Varga in 1962. Essentially, this condition is a generalization of the Feingold and Varga definition of block diagonally dominant matrix. The reason why this is a generalization is because Feingold and Varga defined a matrix as block diagonally dominant if the sum of the product of the norm of A inverse and the product of the norm of AJ was less than 1. But of course, you know that the product, a matrix norm is characterized by the submultiplicativity property. Therefore, the norm of A times B is less or equal than the norm of A times the norm of B. Therefore, every time the definition of Feingold and Varga of block diagonal dominance is verified, this condition is verified as well. However, there are situations where the condition that we propose is verified, but the condition introduced by Feingold and Varga does not hold. Therefore, our definition of block diagonal dominance is a generalization to a broader class of matrices with respect to the one introduced by Feingold and Varga in 1962. We then tested the performance of Monte Carlo synthetic acceleration using a code implemented in C++. We ran the simulations on Emmet, that is a small cluster at Oak Ridge National Laboratory. And although the cluster has 32 nodes, we actually use only a single CPU node. So we ran the simulations in serial mode. And we also ran the same simulations on GPUs. Again, the number of GPU nodes used is 1. Therefore, in the numerical experiments, we used 1 CPU node and 1 GPU node. The problems that we consider are 2. The first one is a 2D parabolic problem. We generated it with the IFIS toolbox. And here you have details about the space and time discretization for quadrilateral finite elements and finite differences in time. And in slide number 65, you have the setup, the numerical setting. In particular, we used 10 to the minus 7 as a tolerance for the stopping criterion on the relative residual. We use the adjoint Monte Carlo synthetic acceleration as a linear solver. The random walks are truncated after 1,000 steps, or they can be also cut off earlier through a weight cutoff that is set to 10 to the minus 9. We use 0.1 as a threshold for the adaptive selection of the number of random walks to employ, and the adaptive selection of the number of random walks is performed with a granularity of 1,000 random walks. This means that after 1,000 histories, the apparent relative standard deviation is computed, and if the adaptive criterion is not verified, then another batch of 1,000 histories is computed, and this goes on up until the apparent relative standard deviation goes below 0.1. The second, the preconditioner that we use is the IINVA preconditioner, and we apply the preconditioner to the right. This allows us to build an iteration matrix that still is pretty sparse. Indeed, the fill-in with respect to the coefficient matrix is of the order of 4. We have the one norm of H bigger than 1, but if we explicitly build the spectral radius of, if we explicitly compute the spectral radius of H hat, we notice that the spectral radius of H hat is less than 1. Therefore, the adjoint Monte Carlo method is guaranteed to converge. And indeed, MCSA converges in 6 iterations, whereas the equivalent deterministic Richardson iteration will converge in 155 iterations. This significant drop of the number of iterations to converge from the deterministic to the stochastic acceleration shows that most of the time is spent inside of the green box of the MCSA pseudocode that I showed you before, which means that most of the time is spent in the resilient part of the algorithm, that part of the algorithm that can be easily address and deal with hard and soft faults. Here in slide number 67, we show the performance of one node CPU versus one node GPU. Now, I know that the computational times are very high and absurd for a problem of this dimensionality. However, this preliminary study on stochastic accelerations doesn't aim to attain efficiency. It aims to attain resilience, hoping that in the future, further studies will improve the performance and possibly combine efficiency and resilience simultaneously. But here, for now, the goal is resilience. So the computational time is a secondary metric. The real metric is the reduction of the number of iterations with respect to the deterministic algorithm. The second test case is the SPN equation that is generated by discretizing the Boltzmann equation. This matrix was produced with the code given to us by our collaborators at Oak Ridge. And in this case, we apply a block Jacobi preconditioner. Again, we apply the block Jacobi preconditioner to the right. By explicitly building the iteration matrix H, we can still come up with an iteration matrix that is sparse. Indeed, the fill-in factor is only of the order of 2. Again, the one norm of H is bigger than 1, but if we explicitly compute the spectral radius of H hat, we notice that the spectral radius of H hat is less than 1, and so the adjoint Monte Carlo method is guaranteed to converge a priori. And again, the number of iterations to converge is 6 against 652 iterations required by the deterministic Richardson. Again, this drastic reduction of the number of iterations proves that most of the computational time is spent on that part of the algorithm that makes the difference with respect to the deterministic scheme, which means that most of the computational time is spent inside of the green box, the resilient part of the algorithm. Again, comparing the computational time between GPU and CPU, we can see, as before, that the GPU drastically reduces the computational time, even if, speaking in absolute scale, all these computational times are sort of um, not that interesting. All these the studies conducted and presented in these slides have been published by my advisor, my collaborators, and me in a paper called Analysis of Monte Carlo Accelerated Iterative Methods for Sparse Linear Systems on the scientific journal Numerical Linear Algebra and Applications. In conclusion, we can say that Monte Carlo linear solvers are appealing to address resilience. However, the convergence is difficult to be guaranteed, but promising preliminary results have been obtained using a inv or a block preconditioner as a preconditioner. In the future, it's important to extend to possibly explore other classes of matrices with respect to the one that we have already found, for which Monte Carlo linear solvers can be guaranteed to converge a priori, and also analyze deeper the connection between the spectral radius of H and the spectral radius of H hat, and maybe also come up with more sophisticated adaptive criteria to select the number of histories to compute. And this concludes the lecture number 2. And at the end of the slides that will be available to you, you have a list of papers that you can read in order to explore both the literature on deterministic and stochastic accelerations for fixed point iterations. With this, I say you thank you very much for attending my online lectures, and I wish you all the very best for your scientific research. Bye.